Picture a glass jar sitting on a wooden table in a quiet room somewhere in rural Kansas. It is an ordinary mason jar, the kind used for preserving summer peaches, for storing leftover screws, for holding pennies. It is sealed. It contains, by any reasonable human account, nothing. Air, atmosphere, the ordinary invisible stuff of breathing and weather. You could hold it in your hand and feel its weight, and the weight you feel would be almost entirely the glass itself. The air inside, the thing that fills it, contributes so little to the total mass that your kitchen scale could not tell the difference between the jar sealed and the jar with its lid cracked open. Now imagine you could remove that air. Slowly, patiently, molecule by molecule, you could pull out every nitrogen atom, every oxygen molecule, every drifting speck of argon, and carbon dioxide and water vapour, until there was truly nothing left inside the glass. You would have achieved something remarkable. You would have created one of the most difficult to produce conditions in the known universe, a perfect vacuum. And you might look at this jar, this sealed glass vessel, now containing nothing, and feel that you had accomplished something absolute, that for the first time in your life, you are looking at genuine emptiness. You would be wrong. Inside that jar, even after every atom has been removed, quantum fields still pulse and flicker. Virtual particles wink in and out of existence so rapidly that they blur the boundary between something and nothing. Energy saturates the vacuum at a density we still cannot fully explain. The jar is not empty. The jar cannot be empty. The universe itself will not permit true emptiness, and the lengths to which reality goes to prevent it are among the strangest and most beautiful and most unsettling facts we have discovered in the entire history of human inquiry. But that is just the jar. That is just the smallest possible space you could think to examine. What about the room around it? What about the planet beneath it? And the solar system surrounding that planet? And the galaxy spiraling above it in the night sky? And the billions of galaxies beyond that, stretching to the edge of everything we can observe? What happens when you ask the question not of a mason jar, but of the universe itself? The answer is this: the universe is so empty, and the matter within it so impossibly sparse and isolated that the word empty does not begin to describe it. We need different words. We need different ways of thinking. And when we find them, when we actually follow the mathematics to its conclusion and sit with what it means, something shifts. The solidity that seemed to define reality turns out to be a brief, local, almost accidental exception to an overwhelming rule of absence. This is the story of that absence. This is the story of the void the universe is mostly made of, and what it tells us about everything we think we know, about the nature of matter, space, and existence itself. We begin, as most of the universe's stories begin, with a single atom. In 1897, in a cramped laboratory at the Cavendish in Cambridge, a man named J. Thomson was passing cathode rays through electric and magnetic fields, watching the beams deflect, measuring the angles. He was trying to understand something that had puzzled physicists for years: the nature of the particles streaming off heated metal when voltage was applied. What he found, or rather, what he concluded from his measurements on that series of Tuesday and Thursday afternoons over several months, was that these particles were far lighter than any atom. They were, in fact, fragments of atoms, pieces of the supposedly indivisible. He had discovered the electron, His model of the atom, proposed shortly afterward, was reasonable given what he knew. Electrons were embedded throughout the atom, like raisins in a pudding, spread out, evenly distributed, filling the entire volume. The atom was a solid thing, dense, full of itself in the way that matter seemed, intuitively, to be full. Thomson called it the plum pudding model, and it had a kind of Victorian solidity to it, a sense of things being properly occupied and properly arranged. 12 years later, in 1909, one of Thomson's former students, a New Zealander named Ernest Rutherford, working now at Manchester, conducted an experiment that would dismantle that picture entirely. Rutherford had his assistant, Hans Geiger, and a young undergraduate named Ernest Marsden fire alpha particles at a sheet of gold foil and record where the particles landed on a fluorescent screen wrapped around it. The logic was simple. If Thomson's model was correct, the positive charge would be spread throughout the atom, and the alpha particles, themselves positively charged, would be deflected slightly, but pass through. Like bullets through a fog bank, minor deflection. Mostly through, most of them did pass through. That part was expected. But a small fraction, 1 in roughly 8,000, bounced back almost directly the way they had come. Rutherford later described his astonishment by saying it was as if you had fired artillery shells at tissue paper and some had come back and hit you. He sat with this result for months before he understood what it meant. The positive charge of the atom and almost all of its mass was concentrated in a region unimaginably smaller than the atom itself, a tiny, dense, furiously compact nucleus surrounded by almost nothing, a vast empty orbit through which the electrons moved, distant and ghostly. The atom, it turned out, was almost entirely empty space. Rutherford spent the year of 1910 working through the consequences, and his conclusion was this: the nucleus of the gold atom occupied a volume roughly 100,000 times smaller than the atom itself. If you scaled an atom to the size of a cathedral, say the Cologne Cathedral, one of the largest Gothic cathedrals in the world, the nucleus at the centre would be about the size of a grain of rice. A single grain of rice sitting on the floor of a cathedral whose walls are so far away you can barely see them in the dim light. And between the rice grain and the cathedral walls, nothing. Not gas, not fluid, not any kind of material medium. Just empty space with electrons somewhere out near the walls, moving so fast and in such strange quantum orbits that they can't be located at any particular place, but only described as a probability cloud, a smear of likelihood that the electron might be here, or here, or here. Rutherford published this picture in 1911, and it struck many of his contemporaries as almost paradoxical. If the atom was mostly empty, why did matter feel solid? Why didn't your hand pass through a table? The answer, which took several more decades of quantum mechanics to fully work out, was that electrons are bound to their atoms by the electromagnetic force, and when the electron clouds of adjacent atoms approach each other, they resist being compressed together, not because of any physical contact in the classical sense, but because quantum mechanics forbids two electrons from occupying the same quantum state simultaneously. This is the Pauli exclusion principle formulated by Wolfgang Pauli in 1925, and it is the ultimate source of the solidity of matter. Atoms resist compression not because they are full, but because the quantum rules governing electrons prevent overlap. The hardness of the table is, at its root, a consequence of a mathematical rule about the indistinguishability of fermions. Consider what that means for the object you're sitting on right now. The chair beneath you, the floor beneath that, the building surrounding you. All of it is atoms, and atoms are almost entirely empty. If you took all the actual matter out of all the atoms in the human body, all the protons and neutrons and electrons stripped of the space between them and compressed into direct contact, the entire mass of a human being would fit in a volume smaller than a grain of sand. All 7 billion people who have ever lived at any one time on this planet, compressed this way, would fit comfortably inside a sugar cube. The solidity you feel beneath your hands right now is not matter touching matter. It is the electromagnetic force, the mutual repulsion of electron clouds pushing back against your weight. You are not sitting on anything solid. You are floating, in the most technical sense, on a field of mutual electrical resistance between mostly empty structures separated by vast quantum distances. The hardness of granite, the resistance of steel, the density of bone, none of these arise from matter being full. They arise from emptiness arranged in configurations that push back, and yet we have barely started. The atom's interior is only the beginning of the vacancy. Before we go further, take a moment to consider something equally astonishing about the world you live in right now. The digital world, the one you use to navigate information and communication and experience. If the universe is vast and difficult to grasp, the tools we use to explore it are becoming increasingly capable. This script is brought to you by Brilliant, a platform dedicated to building real mathematical and scientific intuition through interactive learning. Brilliant's approach is not the passive absorption of facts, but the active construction of understanding. You work through problems, build models, test your comprehension, and emerge with knowledge that actually sticks. What makes Brilliant particularly relevant to the ideas we're exploring today is their astrophysics and quantum mechanics courses, which walk you through the actual mathematics behind atomic structure, quantum fields, and cosmological scales. When Rutherford's experiment produces those astonishing deflection statistics, Brilliant lets you work through the cross-section calculations yourself. When we talk later about the density of matter in the cosmic web, you can go build your intuition for orders of magnitude and exponential scaling in their foundational math courses. The best science documentaries in the world can ignite a curiosity. Brilliant is what you use to feed it properly. If you go to brilliant.org and try their free trial for 30 days, you will find more than 10,000 lessons in math, science, and computer science designed to take you from wherever you are to somewhere genuinely new. The first 200 people to use the link in the description will get 20% off an annual premium subscription. Brilliant. Actually learn this. Let us leave the atom and zoom outward. Let us ask a different question. Not how empty is matter, but how empty is space itself. The solar system feels intuitively like a reasonably populated place. We have a sun, 8 planets, dozens of moons, hundreds of thousands of asteroids, millions of comets drifting through the outer dark. It feels like a neighborhood, if not a crowded one. And yet, if you wanted to build a scale model of the solar system in a field somewhere, and you made the sun the size of a grapefruit, roughly 4 inches across, here is what you would find. Mercury would be a grain of sand about 16 feet away. Venus, another grain 30 feet out. Earth, a slightly larger grain 42 feet from the grapefruit sun. Mars, a tiny speck 64 feet. And then you would start walking. Jupiter, the largest planet in the solar system, a sphere about the diameter of a large marble at this scale, would be 220 feet away from your grapefruit sun. Saturn, another marble, 400 feet. Uranus, 6/10 of a mile. Neptune, nearly a full mile. And beyond Neptune, the Kuiper belt stretching out for another mile or two of model space. And then the Oort cloud, the distant halo of comets and ice that marks the very outer edge of the sun's gravitational reach, would extend for another 2,000 miles. At this scale, New York to the middle of the Pacific Ocean, just to model one solar system, with a grapefruit at one end, and essentially nothing in between. Almost everything in the solar system is not solar system. Almost everything is the void between objects. In actual physical terms, the mean density of matter in the solar system, if you took all the mass and spread it evenly through the volume of space the solar system occupies, is approximately 0.0000000000002 grams per cubic centimetre. That is 2/10 trillionths of a gram per cubic centimetre. A cubic centimetre of water, for comparison, contains 1 gram of matter. The solar system, on average, contains matter at a density roughly 5 trillion times less than water. Think about that in the context of the most isolated experience a human being has ever had. In December 1968, the crew of Apollo 8, Frank Borman, Jim Lovell, and William Anders, became the first human beings to travel beyond Earth's gravitational influence and enter the gravitational domain of another world. They spent 3 days crossing the 384,000 kilometers between Earth and the Moon, and when they arrived and slipped behind the lunar limb and cut the radio connection to mission control, they were the most isolated people in human history. On Christmas Eve, William Anders looked out the small porthole and photographed Earthrise, the first photograph of the Earth hanging in the black void above the Moon's horizon. Borman later said that the overwhelming impression was not the Moon but the Earth. How small it was, how fragile, how alone it looked in all that darkness. The three of them were moved to tears in alternation, and none of them had entirely expected that reaction. They had travelled about a light second from home. 1 light second. The nearest star is 4.24 light years away. That is more than 130 million times farther than the Moon. The entire human experience of space travel, every kilometre of journey we've ever made, has covered a distance that is 130 million times smaller than the gap to our nearest stellar neighbour. The void is not out there. The void begins just past the edge of your atmosphere. We just have not been deep enough into it yet to feel its full weight. And the solar system is extraordinarily dense by cosmic standards. It is a rich, crowded, over-dense pocket of reality compared to what lies beyond it. Step back further. Step back to the scale of stars. In 1838, a German mathematician and astronomer named Friedrich Wilhelm Bessel spent months analysing the minute wobble of a star called 61 Cygni, a faint double star in the constellation of the Swan. And from that wobble calculated something no human being had ever calculated before. He measured the parallax of the star, the tiny apparent shift in its position as the Earth moved from one side of its orbit to the other. He spent the better part of a year making these measurements with extraordinary care, accounting for every instrumental error he could conceive of, checking and rechecking, and then he published his result. 61 Cygni was 10.3 light-years away, 10.3 years of light travel time. Even accounting for the slight imprecision of his early method, the modern value is 11.4 light-years. Bessel had glimpsed the truth of stellar distances for the first time. He had looked at a point of light in the sky and determined that the light reaching his eye had left its source more than 10 years before it arrived. That the star he was seeing was not where it appeared to be, that it was somewhere it had been a decade ago. It is worth pausing here to feel the full weight of what Bessel had discovered. Not just the number, not just the distance, but the temporal implication. The star he measured had moved, in the years since its light departed, to somewhere else. He was, in a precise and literal sense, looking at the past. The sky's not a map of where things are. The sky is a map of where things were, each star at a different moment of history, some moments separated from us by years, some by centuries, some by millions and billions of years. The night sky is a temporal mosaic, a window into multiple different eras of the universe displayed simultaneously. The light from a nearby star from last decade mixed with light from a distant galaxy from the early universe, all arriving at your eye in the same instant. A light year is just under 10 trillion kilometers. 10 trillion. If you try to drive to 61 Cygni at highway speed, say 100 kilometers per hour, and you never stopped, never slept, just drove forever into the darkness between stars, the journey would take you approximately 100 billion years, roughly 7 times the current age of the universe, and 61 Cygni is one of the nearest stars to us, one of our cosmic neighbours. The nearest star of all, Proxima Centauri, is 4.24 light-years away. The New Horizons spacecraft, which launched in 2006 and is currently the fastest human-made object ever built, is travelling at roughly 58,000 kilometers per hour. At that speed, it would take approximately 78,000 years to reach Proxima Centauri. If our ancestors had launched it when they first crossed into North America, it would only now be arriving. And Proxima Centauri is extraordinary among stellar objects in that it is classified as our nearest neighbour. If the Milky Way is a city, Proxima Centauri is the house next door. The next nearest star systems after Proxima are the binary pair Alpha Centauri A and B, slightly farther away, and then Barnard's star at about 5.9 light-years, and then a succession of red dwarfs and white dwarfs stretching outward. Within 10 light-years of the Sun, there are roughly 12 known stellar systems. In a sphere of space, 10 light-years in radius, a sphere with a volume of over 4,000 cubic light-years, there are 12 stars. To put it another way, each star in this neighbourhood has an average volume of roughly 350 cubic light-years all to itself. 350 cubic light-years of space, and one small point of burning gas to show for it. Between us and Proxima Centauri, essentially nothing. A few hydrogen atoms per cubic centimetre. The occasional drifting molecule of gas. Interstellar space is not merely sparse, it is a vacuum so deep that the best vacuum chambers on Earth are crowded by comparison. The vacuum of interstellar space contains roughly 1 atom per cubic centimetre on average. In the most carefully engineered vacuum chambers at facilities like CERN, the density is still around 10,000 molecules per cubic centimetre. Outer space is 10,000 times emptier than the emptiest thing we can make, and yet this gives you the wrong impression. 1 atom per cubic centimetre sounds like almost nothing, but it is vastly more than average. That number applies to the interstellar medium within a galaxy. The density of matter in a galaxy is already far higher than the cosmic average. When we zoom out to the scale of the universe itself, even a lone hydrogen atom per cubic centimetre would represent unimaginable abundance. Let us talk about the Milky Way, our galaxy, our home. The Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty in that number, a range of 300 billion stars, is itself larger than many estimates of the entire galaxy's population. And we are uncertain by that much because counting stars in a galaxy you are embedded in, surrounded by dust and gas and the blinding brightness of the galactic centre, is extraordinarily difficult. So let us say 200 billion for the purposes of thinking. 200 billion suns, scattered across a disk roughly 100,000 light-years in diameter and perhaps 1,000 light-years thick in the outer regions and several thousand thick toward the bulge. If you spread those stars evenly through that volume, which they are not, but if you did, the average distance between stars would be roughly 5 to 6 light-years. Call it an average of 1 star per small sphere of space, about 10 light-years across in every direction. In a sphere 10 light-years in radius, 1 star. Everything else, nothing. The Milky Way itself has a particular structure that makes its emptiness both more interesting and more layered than the simple average suggests. The galaxy is not a uniform disk. It has spiral arms, vast curved structures where star formation is enhanced, where young blue stars blaze brightly and die quickly, where hydrogen gas clouds collapse and ignite and scatter their nuclear ash back into the interstellar medium. Between the spiral arms, the disk is thinner and older, populated by more ancient stars drifting through a relative quiet. Our own sun sits in one of these interarm regions, in the Orion Spur, a minor structural feature on the inner edge of the Perseus Arm, about 27,000 light-years from the galactic centre. We are not in the thick of anything. We are in a relatively quiet corner of a suburban spiral. At the galactic centre, the density of stars increases dramatically. Within a few light-years of the central supermassive black hole, Sagittarius, a star with a mass 4 million times that of the Sun, stars crowd together at separations of light weeks, or light months, rather than light years. The night sky, as seen from a planet near the galactic centre, would be a blaze of light, with hundreds of brilliant stars visible at all times. Some close enough to be seen as disks rather than points. The entire background of space incandescent with stellar light. Life there, if it existed, would have a very different sense of cosmic loneliness than we do. From our vantage point, most of the galaxy is invisible to us in ordinary light because of the dust lanes in the disk. We see the Milky Way as a faint band across the night sky, the integrated light of billions of distant stars blurred by distance and obscured by dust, and the centre as an opaque region in Sagittarius, where the dust is so thick that visible light cannot penetrate it at all. We have to use radio waves and infrared to see through to the core. But much of the volume of the Milky Way is not even close to the star-filled disk. The galactic halo, the vast dark spherical region extending perhaps 200,000 light-years in every direction around the galactic center, contains relatively little ordinary matter at all. It is suffused with dark matter presumably, and threaded with ancient stars from early epochs. But in terms of atoms and molecules and the ordinary material of the world, the halo is extraordinarily thin and cold and empty, and around the Milky Way, more nothing. The void between galaxies, intergalactic space, the distance between the Milky Way and the Andromeda Galaxy, our nearest large galactic neighbour, the one we are gravitationally bound to and will eventually merge with in roughly 4.5 billion years, is approximately 2.5 million light-years. 2.5 million years of light travel. If the Milky Way were a dinner plate, Andromeda would be another dinner plate sitting 2.5 feet away. And between them, almost nothing. A thin, cold scattering of gas drifting in intergalactic space. Perhaps one atom per cubic meter. One atom per cubic meter. A box about the size of a washing machine, and one atom rattling around inside it somewhere. Not one atom per cubic centimetre. One atom per cubic metre. 10,000 times less dense than even interstellar space within a galaxy. The two galaxies together, along with the Triangulum galaxy and a retinue of smaller dwarf galaxies and globular clusters, constitute what we call the local group, a gravitationally bound collection of roughly 50 galaxies spread across about 10 million light-years. The local group is itself part of the Virgo supercluster, which is part of the Laniakea supercluster, a structure discovered and named in 2014 by Brent Tully of the University of Hawaii and his colleagues, stretching across 520 million light-years and containing the mass of roughly 100 million billion suns. And Laniakea is one of millions of such structures. The universe contains superclusters in vast numbers, and between the superclusters, the voids. In 1989, in a corner of the Harvard Smithsonian Center for Astrophysics, two astronomers named Margaret Geller and John Huchra published a paper that contained a map. It was a simple map by the standards of what would come later, a two-dimensional slice of the sky showing the positions of galaxies out to about 650 million light-years. Geller had been working with Huchra for years on the Center for Astrophysics Redshift Survey, measuring the spectra of thousands of galaxies, calculating from the redshift in their light how fast they were receding and therefore how far away they were. When the map appeared in the November 17th issue of Science, it produced an effect that Geller later described as almost physical in the people who looked at it. Because the galaxies were not scattered randomly, they were not spread evenly through space like raisins through a loaf. They were gathered into long, thin filaments, curved sheets and strings of galaxy clusters, surrounding enormous empty spaces. The map looked like foam. It looked like the cross-section of a sponge, or the structure of soap bubble pressed together. Dense walls of galaxies surrounding vast dark voids where there was essentially nothing. Geller and Huchra called the largest structure in their map the Great Wall. It was a thin sheet of galaxies roughly 500 million light-years long, 300 million light-years wide, and only 15 million light-years thick. a vast curved membrane of matter stretched across an enormous portion of the observable universe, and surrounding the Great Wall, and surrounding every other filament and sheet of galaxies in the map, the voids. The voids are the most under-discussed feature of the large-scale universe. They are the parts of maps that contain nothing, and human attention tends not to linger on nothing. But the voids are where almost all of the volume of the universe actually lives. Cosmologists have since identified and catalogued hundreds of enormous voids, regions of space where galaxy density drops to nearly zero, lasting for hundreds of millions of light years in every direction. The Boötes void, discovered in 1981 by Robert Kirshner and his colleagues at the Harvard-Smithsonian Center for Astrophysics, was among the first and most shocking. It is approximately 330 million light-years in diameter. Inside it, there are very few galaxies, just a handful, and they may be chance superpositions or intruders from the edges. The Boötes void is essentially empty of galaxies. It is, in terms of the cosmic web structure, a bubble, a region where matter simply never gathered, never condensed, never formed the gravitational seeds of structure. 330 million light-years of nothing. If our galaxy were located at the center of the Boötes void, we would not have discovered any other galaxies until the 1960s, because the nearest ones would still be too far away for earlier telescopes to see. Think about that for a moment. An emptiness so vast that an entire civilization of astronomy would have looked out for thousands of years and seen only stars, only the Milky Way, and believed itself to be alone in the universe, not from philosophical presumption, but because there was genuinely nothing nearby to find. And the Boötes void is not even the largest void we know of. The Hercules Corona Borealis Great Wall, a structure discovered in 2013 and subsequently debated in the literature, may be associated with a supervoid stretching over 10 billion light-years. 10 billion light-years, a tenth of the observable universe's diameter, where matter is almost entirely absent. But the voids are not simply absences. They are not just the universe's leftover space. Cosmologists have come to understand that voids are active participants in the evolution of structure. Their emptiness is not accidental, but is the result of specific physical processes operating from the earliest moments of the universe. The current model of cosmic structure formation holds that the tiny quantum fluctuations in the density of the early universe, fluctuations so small they were measured in parts per 100,000, were amplified by gravity over billions of years into the web we see today. Regions that were slightly overdense attracted more matter, grew denser still, eventually collapsing into the galaxies and clusters we see. Regions that were slightly underdense were drained of matter by their denser neighbours, and as matter flowed outward from them into the surrounding filaments, the underdense regions grew less dense. They expanded and emptied. The voids are the scars of the early universe's density map, the places where the initial quantum fluctuations happened to be slightly below average, and gravity then hollowed them out over cosmic time into the vast empty bubbles they are today. This is a stunning fact. The large-scale emptiness of the universe is the amplified echo of quantum physics in the first moments after the Big Bang. The void is the grown-up version of a quantum fluctuation. The largest structures we know of, the emptiest regions of the observable universe, trace their origin to events at the smallest scales physically conceivable. Here is where the mathematics becomes genuinely staggering, and where you have to sit still for a moment and let it arrive. The observable universe is approximately 93 billion light-years in diameter. It contains an estimated 2 trillion galaxies, a number revised upward dramatically in 2016 by a team led by Christopher Consolis at the University of Nottingham, who analysed images from the Hubble Space Telescope and extrapolated from what Hubble couldn't quite see to produce a census of the entire observable volume, 2 trillion galaxies, each containing, on average, perhaps 100 billion stars. That is 200 sextillion stars, 2 times 10 to the 23rd power, a 2 followed by 23 zeros. And yet, those 200 sextillion stars, with all their mass, with all their planets, and moons and asteroids and comets and gas and dust, constitute approximately 5% of the total energy content of the observable universe. Ordinary matter, atoms, molecules, everything that glows and absorbs and has mass in the way we mean when we say matter, is 5% of what's out there. Dark matter accounts for another 27%. And dark energy, the mysterious accelerating pressure that is pushing the universe apart at an ever-increasing rate, comprises the remaining 68%. So even if we set aside dark matter and dark energy and focus only on ordinary matter, 5% of the universe's energy content spread across 93 billion light-years of space. The average density of ordinary matter in the observable universe works out to roughly 6 protons per cubic meter. 6 protons per cubic meter. 6 hydrogen nuclei, particles with no electrons to call their own, rattling around in a box the size of a bedroom. That is the average density of matter in the universe. 6 protons per cubic meter is the average. Most of those protons live in galaxies, in stars, in the hot plasma of galactic halos and filaments. Which means the voids, the regions between the filaments, the enormous empty bubbles that occupy the majority of cosmic volume, contain far less than 6 protons per cubic meter. In the deepest voids, the density drops to perhaps 1 proton per 100 cubic meters, 1 proton per room-sized volume, 1 proton per volume greater than many apartments. 1 proton alone in the middle of all that space. If you were somehow instantiated at a random point in the observable universe, if you were quantum teleported to a position chosen uniformly at random from all possible positions in the 93 billion light-year sphere, the overwhelming probability is that you would find yourself floating in a void, surrounded by darkness, with the nearest galaxy 100 million light-years away and the nearest atom several meters from your face. This is not a poetic extrapolation. This is the statistical reality of where matter lives. Now we need to confront something that even professional physicists sometimes struggle to hold fully in mind. The matter that makes up all of this, all of the stars and galaxies and everything else, is itself almost entirely empty. We established this with Rutherford's gold foil experiment. The atom is largely a void, with a tiny nucleus at its centre, surrounded by electrons in distant orbits. But what are those electrons? What is the nucleus made of? And what are those things? In 1964, A physicist named Murray Gell-Mann, working at Caltech, proposed that protons and neutrons were not fundamental particles, but were themselves composed of smaller constituents. He called them quarks, borrowing the word 3 quarks for muster mark from a passage in James Joyce's Finnegan's Wake, partly because the literary reference amused him, and partly because giving absurd names to things that could not be directly observed seemed fitting. Gell-Mann shared the 1969 Nobel Prize in Physics for this work. Quarks come in 6 types: up, down, strange, charm, bottom, top, and they combine in trios to form protons and neutrons. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. They are held together by the strong nuclear force mediated by particles called gluons in a dynamical churning that is among the most energetically intense phenomena in the known universe. Here is something that very few popular accounts of particle physics convey clearly. Most of the mass of the proton does not come from the quarks themselves. The 3 quarks inside a proton contribute only about 1% of the proton's total mass. The remaining 99% comes from the energy of the strong force binding, the gluons and the sea of virtual quark-antiquark pairs constantly flickering in the proton's interior, and the kinetic energy of the quarks themselves, confined in a small space and therefore moving very fast by the uncertainty principle. A proton is, in mass terms, almost entirely made of energy. Its quarks are almost incidental. They define its quantum numbers, its charge, its identity as a proton rather than a neutron or some other particle. But its mass, the property we most associate with ordinary matter, comes from the binding energy of the strong force. E equals mc squared. That equation works in reverse. The energy stored in the strong force, in the confinement of quarks, manifests as mass. The weight of ordinary matter, the weight of rocks and water and bodies and planets, comes almost entirely not from the quarks themselves, but from the energy of the force that holds them together. Matter is mostly energy in disguise. But here is the thing about quarks. They are point particles, or as close to point particles as we can determine. The current experimental upper limit on the size of a quark is about 10 to the minus 18 meters, 1 atometer, 1 billionth of a nanometer. The proton itself, the thing the quarks sit inside, has a radius of about 0.85 femtometers, 10 to the minus 15 meters. The quarks take up, at most, a tiny fraction of the proton's volume. Most of what the proton is not the quarks themselves, but the energy of the strong force binding them, and the virtual gluons constantly flickering between them, and a quantum field soup of quark-antiquark pairs continually popping in and out of existence in the interior. And the electron, even smaller. The electron is, as far as any experiment has ever been able to determine, a true point particle. It has no internal structure. It has no size in the sense of a physical radius that any experiment has ever resolved. The electron is, as nearly as we can tell, a mathematical point, an infinitely small location in a quantum field, defined entirely by its interactions with that field rather than by any extended physical structure. So the atom is a nucleus of quarks held together by energy, orbited at enormous distances by point-like electrons that are themselves patterns in a quantum field, all surrounded by effectively nothing, all held in configuration by forces that are themselves not material at all. Matter, examined closely enough, is not stuff. It is relationships. It is process. It is, in a very technical and precise sense, almost entirely the interactions between things rather than the things themselves. The philosopher of physics, David Albert, has spent decades exploring what this means for our intuitions about the physical world, and his conclusion is essentially that our picture of matter as solid, continuous, extended stuff is a kind of very useful fiction that our sensory systems evolved to construct because it helps us navigate the middle-scale world we live in. At the level of fundamental physics, the fiction does not hold. The chair is not solid. The floor is not solid. You are not solid. These are approximations so accurate at human scales that they are operationally equivalent to truth. But they are not the truth. The question that follows from all of this, the question that has no clean answer and that has tormented cosmologists for decades, is why is there anything at all? Given the vast emptiness of the universe, given the extraordinary sparseness of matter, given that matter itself is mostly absence and force and quantum froth, the question of why there is something rather than nothing is not merely philosophical. It has technical teeth. It is a question with specific physical content. And the specific physical version of it, the one that cosmologists and particle physicists lie awake about, is called the matter-antimatter asymmetry problem. In 1967, a Soviet physicist named Andrei Sakharov, the same Sakharov who would later become the Soviet Union's most prominent dissident and a Nobel Peace Prize laureate, outlined in a short paper the 3 conditions that would be necessary for the universe to contain more matter than antimatter. These conditions are now known as the Sakharov conditions. They require a violation of the symmetry between matter and antimatter in the laws of physics, a violation of certain symmetries related to the reversibility of physical processes, and a period of departure from thermal equilibrium. All 3 appear to be realized in the early universe. The reason the Sakharov conditions matter is this: the Big Bang, as our best models describe it, should have produced equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other completely and produce energy. If the universe had begun with equal amounts of both, they would have entirely annihilated, and the universe today would contain nothing but photons, light, radiation. No atoms, no stars, no planets, no observers to notice. The fact that we exist, that atoms exist, that there is a universe of matter at all, tells us that somewhere in the very early universe, a tiny asymmetry existed in the laws governing matter and antimatter. For roughly every billion pairs of particle and antiparticle, there was 1 extra particle of matter. 1 per billion. The rest annihilated. The entire visible universe, all 200 sextillion stars, all 2 trillion galaxies, everything that exists in the form of ordinary matter, is the residue of that tiny asymmetry, the debris from the annihilation of a universe. We do not fully understand what produced that asymmetry. We know that CP violation, the violation of the symmetry between a particle and its mirror image, charge-reversed antiparticle, occurs in certain processes involving quarks. We have measured it in the decays of particles called kaons and B mesons, but the amount of CP violation in the standard model of particle physics is not nearly enough to account for the observed excess of matter over antimatter. Something else caused it, something we have not yet found. some process in the first fractions of a second after the Big Bang that tip the scales by 1 part in a billion. Several experimental programs around the world are actively trying to find this additional source of CP violation. The T2K experiment in Japan shoots a beam of neutrinos from an accelerator at Tokai to a detector at the Super Kamiokande facility 295 kilometers away, and looks for differences in the way neutrinos and antineutrinos oscillate between types. Initial results, published in 2020, hint at a large CP violation in the neutrino sector. Neutrinos and antineutrinos appear to behave measurably differently. If confirmed, this could be evidence for the leptogenesis mechanism, a process in the early universe that created an asymmetry in leptons, the family of particles that includes electrons and neutrinos, which was subsequently converted into a matter-antimatter asymmetry in baryons, protons and neutrons by other standard model processes. The search is ongoing. The result is not yet definitive, but the possibility is real that the origin of all the matter in the universe, the reason you exist, the reason the Earth exists, the reason there is anything rather than nothing, may be a property of the least massive, fastest moving, hardest to detect particles we know of. A ghostly asymmetry in the behavior of neutrinos, particles so light and so unreactive that 100 trillion of them pass through your body every second without interacting, may be the reason you have a body at all. Every atom in your body is the surviving remnant of a primordial battle that matter lost almost entirely. You exist because of a rounding error in the early universe. The emptiness of the cosmos is not incidental to this picture. The emptiness is what you would expect from a universe almost perfectly cleansed of itself, leaving only the trace, the residue, the statistical noise of a near-perfect annihilation event. The universe is empty because it almost succeeded in erasing itself. But there is another kind of emptiness we have not yet discussed, an emptiness that does not describe the space between stars or the voids between galaxy clusters, an emptiness that describes, in a sense, the fabric of space itself. For most of human history, space was assumed to be passive, a stage, the place where things happened, without itself being one of the things that happened. Aristotle believed nature abhorred a vacuum, and so space was never truly empty. It was filled with a substance called ether, a weightless, invisible medium through which light and gravity propagated. For 2,000 years, the ether was the accepted physical description of space itself. Then, in 1887, two American physicists named Albert Michelson and Edward Morley conducted an experiment in a basement in Cleveland, Ohio. They had built an extraordinarily sensitive interferometer, a device that could detect differences in the speed of light traveling in different directions by measuring the interference patterns of split light beams. If the Earth was moving through a stationary ether, light traveling in the direction of Earth's motion should travel at a different apparent speed from light traveling perpendicular to it. The difference would be small, but Michelson was confident his instrument was sensitive enough to detect it. It detected nothing. The speed of light was the same in every direction. The ether did not exist. Space was not a substance. It was apparently, genuinely empty. A mere absence, a featureless backdrop for events. And then Einstein arrived and complicated everything again. In 1915, Albert Einstein completed his general theory of relativity, the most radical reconception of space and time since Newton. In general relativity, space is not a featureless backdrop. Space, or more precisely space-time, the four-dimensional fabric of the universe, is a dynamical entity. It curves. It warps in the presence of mass and energy. The planet orbits the Sun not because some force reaches across empty space and pulls it, but because the mass of the Sun has warped the space-time around it into a curved geometry, and the planet is simply following the straightest possible path through that curved geometry. What we perceive as gravity is the geometry of space-time. This made space something. Not a substance, not an ether, but something. A field with its own geometry, its own degrees of freedom, its own dynamics. And if space is something, then the question of whether it can be truly empty becomes much more interesting. It cannot. Quantum field theory, the framework that unifies quantum mechanics with special relativity, describes all of space as permeated by quantum fields, one for each type of fundamental particle. The electron field, the quark fields, the photon field, the Higgs field. These fields exist everywhere, at every point in space, at every moment. A particle is not an object that moves through these fields. A particle is an excitation of the field, a ripple, a wave packet, a localized disturbance in the field itself. The electron you think of as a particle is the electron field slightly disturbed. What this means for the vacuum, for empty space, the space with no particles in it, is that the quantum fields are still there. The vacuum is not the absence of fields. It is the ground state of all the fields. And in quantum mechanics, the ground state of a system does not mean the state with no energy. It means the state with the minimum energy allowed by the uncertainty principle. And the uncertainty principle requires that there be some irreducible quantum fluctuation, even in the ground state. The vacuum, therefore, is not empty. It is filled with quantum fluctuations. Virtual particles, pairs of particle and antiparticle, constantly appear from nowhere and annihilate back into nothing, so rapidly that they cannot be directly observed. They exist on the razor's edge of what the uncertainty principle allows. Borrow energy to create a pair of particles. Pay it back by annihilating them. Do it fast enough that the energy debt cannot be detected. These are not metaphorical or hypothetical particles. Their effects are measurable. In 1947, a Dutch physicist named Hendrik Casimir predicted that if you place two uncharged metal plates very close together in a vacuum, the vacuum fluctuations between the plates would be slightly restricted. Only fluctuations whose wavelengths fit between the plates could exist in the gap, while the fluctuations outside would be unrestricted. The pressure of vacuum fluctuations outside the plates would therefore slightly exceed the pressure inside, pushing the plates together with a tiny but measurable force. The Casimir effect, as it became known, was measured experimentally in 1997 by Steve Lamoureux at the University of Washington, confirming Casimir's prediction to within 5%. The vacuum itself exerts a measurable force. The emptiness pushes. There is another experimental confirmation of the quantum vacuum that was discovered even before Casimir's work, though its connection to vacuum fluctuations was only understood afterward. In 1947, Willis Lamb and Robert Rutherford at Columbia University measured a tiny shift in the energy levels of hydrogen, a displacement of the 2s and 2p energy levels that should, according to the Dirac equation, be identical. They found that these levels were not identical. There was a small but precise difference, now called the Lamb shift, of about 1058 megahertz. When Hans Bethe worked out the theoretical explanation a few months later, the answer turned out to be that the electron in a hydrogen atom is not orbiting in a static electromagnetic field, it is jostling. The quantum vacuum fluctuations of the electromagnetic field are constantly buffeting the electron, slightly displacing it from where classical theory says it should be, shifting its energy by just the measured amount. The electron's energy levels are perturbed by its interaction with the vacuum. The Lamb shift was one of the experimental stimuli that led to the development of quantum electrodynamics, QED, the most precisely tested theory in all of physics capable of predicting the magnetic moment of the electron to 11 decimal places. And QED describes at its foundation the interaction of matter with quantum field fluctuations. Even the most successful theory in science is, at its root, a theory about the vacuum and what lives in it. The Casimir effect is the most direct experimental demonstration that empty space is not empty. It is the quantum vacuum, a seething energy state that we experience as nothing because we have no choice but to be embedded within it, no reference frame from which we could observe it as other than the default condition of reality. This brings us to what is arguably the deepest and most troubling unsolved problem in all of physics. It is called the cosmological constant problem, and it sits at the intersection of general relativity, quantum field theory, and cosmology in a way that exposes a catastrophic discrepancy between our two greatest physical theories. Here is the problem. Quantum field theory, when you add up the contributions from vacuum fluctuations of all the known quantum fields, predicts that empty space should contain an enormous amount of energy. The calculation depends on assumptions about how far the theory is valid, but even conservative estimates produce a vacuum energy density vastly larger than anything we observe. The most honest calculation, summing up to the Planck scale, the smallest meaningful length in quantum gravity, predicts a vacuum energy roughly 120 orders of magnitude larger than the observed value, 1 followed by 120 zeros. This is the largest discrepancy between a theoretical prediction and an experimental measurement in the entire history of science. It is not close. It is not within a factor of 10. It is off by a number so large that there is no name for it in common use. Some physicists have spent decades searching for a mechanism that would cancel the vacuum energy precisely. Supersymmetry, the theory that every standard model particle has a partner particle of opposite spin statistics, would, if it were exact, cancel the contributions of bosons and fermions exactly. But supersymmetry is not exact. We know this because the partner particles would be the same mass as their standard model counterparts, and we have not found them. Supersymmetry must be broken, and broken supersymmetry does not cancel the vacuum energy to the required precision. The Large Hadron Collider at CERN has found no evidence of the supersymmetric particles that were expected to appear at its energy scales. The cancellation mechanism, if it exists, remains unknown. Other physicists invoke the anthropic principle. In a multiverse of many vacua, each with different vacuum energy, we necessarily find ourselves in one with a small enough vacuum energy to allow galaxies and stars to form. If the vacuum energy were much larger, the universe would expand too quickly for matter to clump, and there would be no galaxies, no stars, no planets, no observers. We are here, therefore we observe a small vacuum energy. This argument, associated most prominently with Steven Weinberg, has been credited with predicting in 1987, before the observational discovery of dark energy, that the cosmological constant must be small but non-zero. Whether this constitutes a scientific prediction or a philosophical concession remains debated. The observed value, the actual energy of the vacuum as inferred from the observed acceleration of the universe's expansion, is not zero. In 1998, two teams of astronomers, one led by Saul Perlmutter and one led by Brian Schmidt and Adam Rees, announced that they had measured the rate at which the universe's expansion was changing over time. They had expected to measure deceleration, the universe's expansion gradually slowing under the mutual gravitational attraction of all its matter. What they found was acceleration. The expansion was speeding up. Something was pushing outward, overcoming gravity on the largest scales, causing distant galaxies to recede from each other at an ever-increasing rate. All three shared the 2011 Nobel Prize in physics for this discovery. That something was named dark energy, and it behaves exactly like a cosmological constant, a fixed energy density of empty space, uniform throughout the universe, unchanging over time. Its value is extraordinarily small. It is, in fact, almost nothing. But almost nothing spread uniformly across the entire volume of the universe adds up to dominate the universe's energy budget. Dark energy comprises 68% of the total energy content of everything we can observe. So we have two problems stacked on each other. The quantum vacuum should have an energy density 120 orders of magnitude larger than what we observe. What we observe is tiny but non-zero. Something is cancelling the quantum vacuum's predicted energy almost perfectly, but not quite, leaving a remainder so small that it makes the original prediction seem insane. No mechanism exists in physics to produce a cancellation this precise. No symmetry is known that would enforce it. The cosmological constant problem is not a missing footnote in a textbook. It is a gaping wound in our understanding of the relationship between quantum mechanics and gravity, and it has not healed in the quarter century since dark energy was discovered. What dark energy does, in practical terms, is this. It fills every cubic centimetre of space with a tiny repulsive pressure. In small volumes, the volume of a room, a planet, a solar system, even a galaxy, this pressure is completely negligible. Gravity dominates at these scales, holding structures together. But on scales of hundreds of millions of light years and above, where matter is sparse and the cumulative volume is vast, the total dark energy adds up to something that gravity cannot overcome. And because dark energy maintains a constant density as the universe expands, unlike matter, which dilutes as space stretches, its relative importance increases over time. The more the universe expands, the more dark energy there is in total, the faster the expansion accelerates. The universe is caught in a feedback loop of its own vacuum energy, doomed by the emptiness of space to expand forever at an ever-increasing rate. The emptiness of space is not just a passive fact about the universe, it is the universe's engine of destruction. The emptiness of space is not empty, and we do not understand why it has the energy it has. We do not understand why it is not either zero or enormous. We do not even fully understand what it is. Let us take all of this together and ask what the universe's emptiness implies about the future. In 1997, the cosmologist Lawrence Krauss, then at Case Western Reserve University, and Glenn Starkman published a paper with the title Life, the Universe, and Nothing. Life and Death in an Ever-Expanding Universe. They were trying to work out the long-term consequences of cosmological acceleration for the possibility of continued complexity and life. What they found was that the acceleration was not merely an interesting observational fact. It was an existential horizon. As the universe expands and dark energy drives that expansion to accelerate, the distant galaxies are receding from us faster and faster. At a certain distance, currently about 14 billion light-years, galaxies are receding so fast that the light they emit today will never reach us. They are beyond our cosmic event horizon. And because the expansion is accelerating, this horizon is shrinking. Galaxies that are currently just inside the horizon will eventually pass outside it. Not because they are moving faster than light, they are not in a local sense, but because the space between us and them is expanding fast enough that the light trying to cross it is losing ground. Over time, all galaxies outside our local group, the small collection of galaxies including the Milky Way and Andromeda and a few dozen smaller companions, will recede beyond the horizon. They will not merely become too dim to see, they will cease, causally, to exist for us. They will pass permanently out of any possible contact, any possible interaction, any possible knowledge. The observable universe will consist of the local group, eventually merged into a single giant elliptical galaxy, floating in an otherwise empty void. Think about what this means for any intelligence that might exist in the far future. The evidence that the universe was ever other than a single galaxy will be gone. The cosmic microwave background, the afterglow of the Big Bang, currently visible as a faint radio haze in every direction, will have been redshifted by the universe's expansion to wavelengths so long that it will be undetectable. The distant galaxies will have receded beyond the horizon. A civilization arising in that far future will have no observational evidence that the Big Bang occurred, no way to infer that other galaxies once existed, no way to reconstruct the cosmic history that we can read so clearly today. They will inherit a simpler, emptier, more mysterious universe than ours, and all the evidence we currently have of the full truth will have been erased by the expansion of space. We live in a privileged era, an era when the evidence of cosmic history is still accessible. An era when a sufficiently motivated civilization, which we very nearly are, can look out and read the story of the universe in the distribution of galaxies and the temperature of the cosmic background and the abundance ratios of hydrogen and helium. In a few trillion years, that story will be gone. The universe will have expanded it away. Over vastly longer timescales, we are talking about periods measured in trillions and quadrillions of years. The stars in that final galaxy will exhaust their fuel. Star formation will cease. The last stars will cool and die. Protons themselves may eventually decay. The current lower bound on proton lifetime is about 10 to the 34 years, and the universe will likely exceed this, reducing all matter to radiation and a thin soup of subatomic particles. Black holes, the most persistent massive objects, will evaporate via Hawking radiation over periods of 10 to the 67 to 10 to the 100 years, depending on their mass. And then, nothing. Not even nothing. An endless expanse of space with a near-zero temperature, a near-zero density of radiation, a thin quantum haze of particles separated by distances so vast that no two particles will ever interact again. The universe will have returned to a state functionally indistinguishable from the vacuum it arose from, but colder and more expanded and permanently unable to produce complexity. There is a concept called the Boltzmann brain, a thought experiment originally posed by Ludwig Boltzmann in the 19th century to question the statistical mechanics of his own entropy-based cosmology, revived in modern cosmology by discussions of the very long-term future. The idea is this: in a universe that lasts forever and contains even a tiny quantum fluctuation rate in its vacuum, given enough time, any configuration of matter will eventually arise spontaneously by pure quantum chance. Including a functioning brain, complete with false memories of a lifetime, spontaneously assembling from random quantum fluctuations, and lasting for just long enough to have a single conscious experience before dissolving back into the vacuum. If the universe lasts long enough, and there are reasons in some cosmological models to think it might last arbitrarily long, then Boltzmann brains will eventually dominate the population of conscious observers. There will be vastly more randomly assembled minds flickering in the quantum void than there were minds that arose through the ordinary biological evolution of structured matter, which means, by a crude version of the anthropic logic, that you are probably a Boltzmann brain, a random quantum fluctuation experiencing a moment of false continuity, rather than an evolved biological organism with a genuine past. The fact that you seem not to be a Boltzmann brain, the fact that your memories seem consistent and coherent, and that the physics you observe matches predictions made centuries ago, is either evidence that the universe is not old enough or large enough for Boltzmann brains to dominate, or evidence that the reasoning fails somewhere, or evidence that we are genuinely not Boltzmann brains. Cosmologists use the Boltzmann brain problem as a constraint on cosmological theories. Any theory that predicts a universe that would eventually be dominated by Boltzmann brains is, in some sense, pathological, because it predicts that we should almost certainly be Boltzmann brains, and we appear not to be. This is the thermal death of the universe, sometimes called the heat death, though it is better understood as the entropy death, the condition of maximum entropy from which no further work, no further structure, no further life can be extracted. Every physical system will have reached its lowest possible gradient, its most probable configuration, the state from which there is nowhere left to fall. The brief, astonishing episode of stars and planets and living things will have been a fluctuation, a local, temporary ordering of matter and energy in an otherwise vast and permanent and deepening emptiness. The universe began as a hot, dense singularity. It will end as a cold, empty void. The in-between, the 13.8 billion years so far, the trillions of years still to come, the entire story of matter and energy and complexity is the exception. The emptiness is the rule. There is one more layer to this, one more dimension of the void that we have not yet visited, and it is perhaps the most disorienting of all. Before we arrive there, Let us think for a moment about where all this emptiness came from. Because the universe was not always empty. In its first moment, in the first fraction of a second after the Big Bang, the observable universe was compressed into a volume smaller than an atom. The density was effectively infinite by any practical measure. The temperature was unimaginably high. There were no atoms, no nuclei, no protons, no quarks. There was only a soup of fundamental particles and radiation in perfect thermal equilibrium, everything pressed against everything else, the most crowded condition imaginable. How did we get from that to this? How did a universe of essentially infinite density become a universe where the average density of ordinary matter is 6 protons per cubic meter? The answer involves one of the most radical proposals in modern cosmology: inflation. In 1979, on an unremarkable morning in December, a young physicist named Alan Guth was working late at the Stanford Linear Accelerator Center, following up on a problem in cosmology that had been nagging at him. He was thinking about magnetic monopoles, hypothetical particles predicted by grand unified theories to have been produced in enormous quantities in the early universe. If they existed in the quantities theory predicted, the universe should be full of them today. We find no magnetic monopoles. Where had they gone? Guth's insight, which he later described as so exciting that it kept him awake through the night, checking and rechecking his calculation, was that the monopole problem and several other puzzling features of the standard Big Bang model could all be solved by a single mechanism. If the very early universe underwent a brief period of exponential expansion, not the slow, steady expansion we observe today, but a violent, inflationary explosion that doubled the size of the observable universe, perhaps 60 times or more, in an unimaginably brief interval, something like 10 to the minus 32 seconds, then all the magnetic monopoles would have been diluted to essentially zero density by the expansion, and the horizon problem would be solved, and the flatness problem would be solved, and the seeds of structure that grew into the cosmic web would be the quantum fluctuations of the inflaton field, stretched to cosmic scales by the expansion. Inflation is the origin of the universe's emptiness. Before inflation, the observable universe was a tiny, hot, dense patch. After inflation, it was a vast, still hot region of space with its original, dense matter, now spread across distances billions of times larger. The density dropped by a factor that makes the numbers we've been discussing look small. The expansion continued afterward at a slower rate, gravity pulling matter back together into the structures we see. But the fundamental dilution, the reason the universe is mostly void, was done by inflation in the first tiny sliver of cosmic time. Inflation also predicts something deeply unsettling about the structure of reality at the largest scales. If inflation occurred, it almost certainly did not stop everywhere at once. Most versions of inflationary theory predict that inflation is self-reproducing. In regions of space where the inflaton field has not yet decayed, the exponential expansion continues, producing new inflationary regions from the quantum fluctuations of the field itself. Some regions stop inflating and become universes like ours. Other regions continue inflating indefinitely, spawning new stopped regions that are themselves pocket universes. This is eternal inflation, and if it occurred, then our observable universe is one bubble among an effectively infinite sea of other bubbles, each a separate universe, each potentially with different physical laws and constants, separated from us by inflationary space that expands so fast it can never be crossed. The emptiness of our universe in this picture is contained within an even vaster emptiness of inflationary space. Our entire observable cosmos, our 93 billion light-year sphere of 2 trillion galaxies, is a tiny frozen drop in an infinite churning ocean of inflation that never ended. The void within our universe is nested inside a larger void that is not even a void in our sense. It is a different phase of reality entirely, one that we could never enter, never observe, never interact with. This is the multiverse of eternal inflation, and it is distinct from the many worlds multiverse of quantum mechanics. They may both be true, in which case the structure of reality has at minimum 2 levels of branching. The cosmological branching of eternal inflation producing pocket universes, and the quantum mechanical branching of the many worlds interpretation producing parallel histories within each pocket universe. The emptiness is not just an observable fact about our universe. It may be a local property of an infinitely larger structure that dwarfs even the emptiness we have been describing. In 1957, a young doctoral student at Princeton named Hugh Everett III submitted a thesis proposing what he called the relative state interpretation of quantum mechanics. His advisor, John Archibald Wheeler, found the idea simultaneously fascinating and difficult to accept, and spent months helping Everett sharpen the argument before approving the dissertation. The physics establishment largely ignored it for years. Today, Everett's interpretation, better known as the many worlds interpretation, is taken seriously by a significant fraction of theoretical physicists, including some of the field's most distinguished practitioners. The many worlds interpretation says this: in quantum mechanics, physical systems exist in superpositions of states. A particle can be spin up and spin down simultaneously. A photon can be polarized in multiple directions at once. A radioactive atom can be both decayed and undecayed. When we make a measurement, one outcome is realized and the others disappear. In the standard interpretation, the wave function collapses, the superposition resolves into a definite outcome, and the other possibilities vanish. Everett asked, what if they do not vanish? What if every possible outcome of every quantum measurement is realized in a branch of the wave function that continues to evolve alongside all the other branches? What if the universe does not choose when a quantum event occurs, but instead branches one branch for each outcome, each branch containing an observer who sees a different result? This is not a metaphor. It is not a philosophical speculation. It is a straightforward mathematical consequence of taking the equations of quantum mechanics seriously as a complete description of physical reality, without adding any additional postulate about wave function collapse. The branching is what the mathematics describes. Everett was essentially asking whether we should believe the mathematics. The majority view among physicists for much of the 20th century was that the wave function did collapse, that the mathematics was telling us something that required an additional interpretive rule, the Copenhagen interpretation, associated with Niels Bohr, which held that quantum mechanics was a theory of observations rather than of underlying reality, and that asking what was really happening between measurements was a category error. Bohr and his colleagues essentially told physicists to shut up and calculate, to use the formalism to predict experimental outcomes, and not to worry about what it meant for the nature of reality. Everett disagreed. He thought that physics should describe reality, not just observations, and that if the mathematics produced branching wave functions, then branching was what occurred. His thesis was initially met with polite incomprehension, revised at Wheeler's urging into a shorter and more cautious form, and then largely ignored. Everett himself left physics and spent his career as a defense consultant and operations researcher. He died in 1982 at the age of 51, having drunk himself to death, reportedly with some awareness that his physics was finally receiving the attention he believed it deserved. Today, the many worlds interpretation is taken seriously by some of the most rigorous thinkers in quantum foundations: David Deutsch at Oxford, Sean Carroll at Johns Hopkins, Max Tegmark at MIT. Carroll, in particular, has argued that many worlds is the only interpretation that takes the mathematics of quantum mechanics fully seriously, without adding additional rules or interpretive glosses. The other branches are not less real than ours. They are not possible in some attenuated philosophical sense. They exist in the same mathematical sense that our branch exists. They simply do not interact with us because the branching process produces states that are orthogonal in Hilbert space, and orthogonal states do not interfere. If the many worlds interpretation is correct, then the universe we live in, the 93 billion light-year observable sphere of stars and galaxies and voids and dark energy, is not the universe. It is a branch, a single history, one outcome among an effectively infinite branching structure of all possible outcomes of all quantum events since the Big Bang. The other branches are not elsewhere in space. They are not distant. They are separated from us by a different kind of distance, a distance in Hilbert space, the abstract mathematical space of quantum states that has no spatial meaning but is as absolute as any spatial separation. The emptiness of our universe, the vast voids, the sparse matter, the cold future, is in this picture one sample from a distribution. Other branches contain different outcomes of quantum events, different patterns of structure formation, different densities of galaxies and different arrangements of stars. The emptiness we observe is specific to our branch. Whether other branches are more or less empty, we cannot say. Whether they have life, whether they have stars, whether they are interesting in any sense, we cannot say and we cannot check, and it may not be possible in principle to ever check. The many worlds interpretation, if true, suggests that the emptiness of our universe is not the emptiness of a unique and solitary container, but the emptiness of one possible outcome of quantum mechanics, running alongside effectively infinite other outcomes, all equally real, none communicating with the others, all expanding and cooling and eventually reaching their own heat deaths in perfect isolation from each other, in parallel forever. There is a version of the question, why is there something rather than nothing, that this makes more urgent, not less. Why this something? Why this branch with its particular emptiness, its particular matter, its particular constants of nature? In the many worlds picture, the question does not go away. It becomes, why does this branch have the properties it has? And the answer might be that we are here to ask because only branches with these properties permit beings who can ask. This is the anthropic principle, and it is either a deep insight about the nature of scientific explanation or a near tautological cop-out, and the physics community has not agreed on which. Come back now to the mason jar on the table in Kansas. We sealed it. We removed all the air from it. We thought we had achieved emptiness. And then we discovered that the jar is threaded with quantum fields, alive with vacuum fluctuations, populated by virtual particles, and the Casimir pressure of the quantum vacuum and the cosmological constant energy that suffuses all of space uniformly and inescapably. But now take the jar and put it back in context. Put it in the room, and put the room in the building, and put the building on the planet, and put the planet in the solar system, with its vast distances and its grapefruit sun, and its marble planets separated by miles of model nothing. And put the solar system in the galaxy, each star 6 light years from its neighbour on average, swimming in interstellar space 1,000 times emptier than the best vacuum chamber we can build. And put the galaxy in the local group, Andromeda 2.5 million light years away, with essentially nothing between us. And put the local group in the Laniakea supercluster, itself one of millions of superclusters, and put all of that in the cosmic web, the filaments and sheets of galaxies surrounding vast voids, hundreds of millions of light years across, where one hydrogen atom per cubic meter drifts for cosmological eternities without meeting another. And remember that all of this, all the matter, all the stars, all the atoms, is 5% of the universe's energy budget, and that the atoms are themselves mostly force and field, the quarks essentially point-like, the electrons mathematical abstractions without spatial extent, and that the universe is accelerating toward a heat death from which no structure will ever again emerge, and that this universe began as a brief cessation of inflation that inflated our tiny patch of space from subatomic scales to cosmic ones, and that this universe may be one branch among infinite branches in a quantum multiverse that has no center and no edge and no special status for any of its histories, and that the matter in it exists because a 1 in a billion asymmetry prevented a perfect annihilation. And now, hold that jar in your hand. The weight you feel is electromagnetic force pushing against electromagnetic force. The glass you see is photons scattering off electron clouds in configurations so regular and so tight that we call them solid. The air you breathe is nitrogen and oxygen molecules separated by distances large compared to the molecules themselves, jostling in a gas that feels continuous but is mostly gap. All of this appears solid and full and present because your sensory systems evolved to navigate a middle-scale world where the approximation of solidity is useful and the underlying vacancy is invisible. The jar is mostly empty. The room is mostly empty. The planet is mostly empty. The solar system is mostly empty. The galaxy is mostly empty. The universe is almost entirely empty. And the emptiness itself, the vacuum, turns out to be something saturated with energy and fields and quantum fluctuations, so that even the nothing turns out to be a kind of something. And we do not know why. We do not know why the vacuum has the energy it has. We do not know whether there are other universes in which it has different values. We do not know what dark energy is, or why the cosmological constant has the value it has, or what happened in the first moments after the Big Bang to produce the matter-antimatter asymmetry that left us here to ask these questions. What we know is that existence is the exception, that matter is rare, and structure is rare, and life is vanishingly rare against the backdrop of the cosmic void. That you, reading this or listening to this, are a fantastically improbable arrangement of quantum fields in a corner of a galaxy in a universe that is overwhelmingly, almost perfectly, almost timelessly empty. That the atoms in your body were forged in stellar furnaces over billions of years and will eventually disperse back into the interstellar medium and drift apart and become, once more, the sparse and wandering raw material of a thinning cosmos. That between the moment of your formation and the moment of your dissolution, you are the universe briefly, locally, temporarily aware of itself, matter organized into the shape of a question, asking about the void it emerged from and will return to. The philosopher Blaise Pascal, writing in the 17th century in his collection of notes published posthumously as the Pensée, described his terror at the silence of the universe. The eternal silence of these infinite spaces, he wrote, fills me with dread. Pascal did not know about quantum fields, or galactic voids, or dark energy, or the Sakharov conditions. He was responding to the nascent awareness, just beginning to enter European consciousness through the work of Copernicus and Galileo and Kepler, that the universe was vast and humanity was small. He felt the vertigo of scale before the tools to measure that scale had fully arrived. We now have those tools. We have measured the void. We have gone back to the foundations of matter and found more void inside the matter. We have looked out to the largest scales and found that structure is the exception and emptiness is the rule. We have looked at the vacuum and found it inhabited by ghost particles and quantum fields. We have looked at the future and found it trending inexorably toward maximum entropy and ultimate darkness. We have every reason Pascal had to feel dread and 100 new reasons he could not have imagined. And yet, the dread is only one possible response. The other response, the one that seems at least as justified, if not more, is wonder. Not the consoling kind of wonder that turns the cosmos into a comforting backdrop for human significance, but the harder kind. The kind that acknowledges the scale and the emptiness and the improbability and says yes, and look at us anyway. Look at the tiny, brief, improbable exception we are. Look at the fact that the universe arranged itself so that in one small corner of one galaxy among 2 trillion, in one moment of one era of the universe's vast timeline, something arose that could ask where it came from. The universe is not mostly full with occasional gaps. The universe is mostly empty with occasional miracles. You are one of the miracles. And miracles, by definition, do not explain themselves. There is a physicist, not a famous one, not a name you would find in textbooks, who once said in a seminar that the question we should really be asking is not why the universe is empty, but why we are so consistently surprised to find that it is. We carry, he said, a deep intuition that reality is full, that the world is rich and dense and occupied. That presence is the default and absence is the deviation. This intuition is wrong. It has always been wrong. The void predates the matter, and the void will outlast it. The old instinct, the one that says matter is the substance and emptiness is the absence, has it exactly backwards. Emptiness is the ground state. Matter is the disturbance. The universe, at its largest and its smallest scales, is a quantum vacuum that briefly, improbably, extravagantly disturbed itself into galaxies and stars and planets, and the kind of complex nervous arrangements of atoms that wonder where they came from. That jar on the table is still there. The table is still there. The room is still there. The ordinary, solid, present, occupied world is still there, and it is still real, and it is still the only world we have. Nothing about the emptiness beneath it diminishes it, but something about understanding the emptiness changes the character of your amazement at it. Because now, when you hold that jar, you are not holding glass and air. You are holding a brief local exception to the rule of the void. You are holding the universe's improbable decision to exist rather than not, concentrated into a small vessel you can hold in your hands. The emptiness around it, and within it, and beneath it, is not threatening the jar's existence. It is, in some sense, the context that makes the jar's existence visible. The universe is almost entirely empty, almost entirely nothing, and the almost is everything. You've been watching the terrifying truth about how empty the universe really is. Don't forget to like and subscribe.